some more detail? What is kinetic energy? What is potential energy?
Kinetic is that energy of motion, and potential is it potentially stable or unstable?
Okay, that's pretty good. Do you have something to add?
Oh, we have to talk about the conservation of mass and energy.
Conservation of mass and energy. Yeah, that's good. Well, in terms of conservation of energy, let's just talk about it here. In terms of potential and kinetic, is there any other energy? Kinetic, potential. I'm sorry? Gravitational energy. Gravitational energy would be thought of as potential energy. So, for example, a stapler that's held up here versus a stapler that's down on the table, could have the same kinetic energy. How would I know they would have the same kinetic energy? Like a stapler up here versus a stapler down on the table. How could I tell that they had the same kinetic energy?
Temperature is the same?
If the temperature is the same? Yeah, exactly. So these would have the same kinetic energy here versus here, but they would have different potential energy. And so gravitational energy is thought of as potential energy, gravitational potential energy. How high or how far from the center of the Earth are you? That kind of thing. That's going to dictate the gravitational. The farther you are, the higher the potential energy. But it's potential energy. We look at different things. We don't look at gravitational. We look at what type of potential energy. I mean, it was explained, but what did I call it? I didn't. What was the word I gave to the potential energy?
Based on how the particles are arranged.
Yeah, it's all based on how the particles arrange, and it's all based on the potential to do something or another, but there was a name given to it. It's not gravitational potential. Chemists aren't that interested in gravitational potential energy, because the difference in gravitational potential energy for, let's say, an oxygen molecule down here versus an oxygen molecule up there is minimal. The reason is its mass is minimal when we're looking at. Gravitational potential energy depends on the mass. Oxygen's not very massive. It is about the electric, but I gave a name to the potential, the type of potential energy we're looking at. What's the name? Nobody has. How about, were there any other types of energy I gave it? There's kinetic, yeah, potential. Anything else? Total energy? Thermal energy? Total energy? Thermal energy? Thermal energy would be kinetic. Did I talk about total energy? The sum of the potential and the kinetic energy, good. And so, yeah, well, that brings us to the conservation of energy, which is the same as the conservation of mass. That is, energy just doesn't disappear and appear, Energy's like atoms, atoms just don't disappear here, Energy's got to come from somewhere or go somewhere. And so when we're looking at different things, the total energy, the total energy sometimes is termed the internal energy. In fact, most of the time it's called internal energy. And the internal energy is just equal to the potential energy plus the kinetic energy. So we could look at a couple of scenarios here just to help reinforce this maybe. An example of this would be, let's say, hot water. Let's say hot water at, let's go with 100 degrees C. All right, now this is water, not steam, so I'll just say H2O liquid at 100 degrees C. L stands for liquid here. Versus H2O liquid at 25 degrees C. Which one has higher energy? The liquid at 100 degrees C or the liquid at 25 degrees C?
100.
At 100 degrees C. Now, relative to 25 degrees C, what do we say? It has higher total energy, right? Does it have higher kinetic energy? Yeah. Does it have higher potential energy? No. It turns out that the potential energy is, well, this is water. And so we have water here, water here. Water has the potential to react, yes. But since it's the same, water and water, what we'll see is that if we cool this down, that is, in other words, this I'm going to write as some arbitrary scale of energy. So the higher up we are here, the higher in energy we are. This would be like gravitational energy in a way, but it's not gravitational energy. This is just showing that this H2O at 100 is going to be higher in energy than H2O at 25. And in order to go from 100 down to 25, there has to be a change in energy. This change in energy is going to equal the change, that's what delta is change in potential energy plus the change in kinetic energy here. So it's the change in potential energy plus the change in kinetic energy. Well, did the potential energy change? When I'm thinking about potential energy is what I term, I don't know if you have this in your notes, but you should have this in your notes. It's chemical potential energy. Chemical potential energy to differentiate between, let's say, gravitational potential energy versus chemical potential energy. You know, chemical potential energy is different. It's not like up higher or anything. Well, here the change in potential energy is 0, and so this change is entirely in kinetic energy. And so if we cool it down, well, that energy is neither created nor destroyed. In other words, the total energy before has got to equal the total energy after. And so if this loses energy, that energy went somewhere. And so that usually, this is that thermal energy that's given off as heat, you know, to cool it down. And so if you have hot water, it's going to cool down. Where does that energy go? It goes into what we call the surroundings. And so the energy goes to the surroundings. And so what happens is the surroundings warms up because of this energy, the surroundings. And so this would be the conservation of energy here. Versus something like this. Another example would be something where we have methane. I have to put in the gas here because it makes a difference, you know. For example, liquid versus gas. If I have H2O liquid at 100 degrees C versus H2O gas at 100 degrees C, they have different energies because there's something else that happens, you know, with that condensation. But here, CH4 gas, if I take a molecule of CH4, I'll need 2 molecules of O2 to combust with it. And so I have a mixture here versus this. Okay, this is going to be at 25 degrees C. And then I'll go to CO2, which is a gas, plus 2 waters. This is going to be at 25 degrees C. And so if I have these two mixtures, methane and oxygen, versus CO2 and water, they're both at the same temperature. If they're both at the same temperature, then we say they both have the same kinetic energy. Even though they both have the same kinetic energy, that doesn't mean move at the exact same speed. It's like, for example, a little car versus a big truck. You know, if you give the same amount of energy to a little car versus a big truck, the little car is going to move a lot faster. You know, than the big truck. The big truck is going to take a lot more energy to get moving. And so that, you know, it doesn't mean that the O2s and the CO2s are moving exactly the same speed, but they'll have the same total energy in terms of kinetic energy. And so the kinetic energy is the same. And so do these have the same energy? Well, we have to look at the potential energy. Now, do these both have the same potential energy? No. If you have a mixture of methane and oxygen versus a mixture of CO2 and water, which one's going to be higher energy? Which one's going to be lower energy? So one way of thinking about this is this could be like sparkling water, you know, CO2 and water. This could be like methane and air. You know, which one do you think? Are they the same energy in terms of chemical potential energy? Or are they different? In other words, if you had let's say if you had a bottle of sparkling water versus a balloon filled with methane and oxygen in your room, which one would you be more worried about, if any? A balloon filled with methane and oxygen, because everybody has memorized that methane is a little bit dangerous because it's flammable and potentially explosive. You know, did you hear about the apartment building that got destroyed? Natural gas explosion. It was a pretty natural gas. This was a pretty recent explosion. Did you see this? Oh, I guess you can't see it. I thought this came on. That's just from a natural gas explosion. That's pretty horrific. The extent of the damage. And so, yeah, natural gas and air is pretty. I don't know how many people died in this one, but that's pretty crazy. And so, a bottle of sparkling water or methane and air, what do you think has higher energy? Well, in terms of potential energy, methane and air might not explode. You know, like for example, if I were to bleed out methane in here, it's not going to explode unless there's a fire or a hot surface. Then there's potential. But right now it's just sitting here at room temperature, so the kinetic energy is there, but potentially it could explode. It's just like if I perch the stapler up here, you know, is that a safe place for it? Seems it's not falling down, so it's not hitting anybody, but if it's sitting up here, it's kind of unstable. And so it's got potential to fall down here, whereas if I put it on the floor, it's safe. And so in terms of potential energy, we call this chemical potential energy. And so it's kind of like gravitational potential energy in the sense that it's just sitting there. It's not necessarily doing anything, but it does have the potential to explode. So that might not have happened. You know, you could have leaked methane out there and hopefully it dissipated. But apparently there was a spark, or a hot surface or a flame that caused it to ignite. And so what we say here is that methane plus 2 oxygens, and I'm going to put the states in here, is like this. This has a high chemical potential energy. I'll just say higher chemical potential. I'm going to abbreviate potential P-O-T-L, energy, E. Then this mixture here is going to be CO2, which I'll put subscript G, which stands for gas, and then 2H2O, subscript L, stands for liquid, in parentheses. This is going to have lower chemical potential energy. So higher, lower. Although the kinetic energy is the same, there's no change here. Because I just wait, obviously there must have been a lot of heat generated there. Boom, a lot of heat. But what we do is we wait. It's not going to stay hot forever. And so we wait for things to cool back down, and then eventually it'll reach back down to 25 degrees C. But I call 25 degrees C what? 25 degrees C is called, well, it's given a special name. It's called room temperature. 25 degrees C. It's a little bit for room temperature, it's a little bit warm. I prefer a room like at 22 degrees maybe. This is like 77 Fahrenheit, which is a little bit warm. Again, energy's on some scale here. And so what we have here is we have conservation of energy. So we start off at high energy, we drop down to low energy. And so the energy doesn't disappear, it goes somewhere. Where did the energy go? Into the surroundings. So there's going to be a drop in energy here. And in this case, if we look at the change in energy, delta E, the change in energy is going to be the change in potential energy plus the change in kinetic energy. Was there any change in the kinetic energy here between where we started and where we end? No. And so the change in kinetic energy for this one, 0. The change was entirely in terms of chemical potential energy. We went from high chemical potential energy to low chemical potential energy, and all that excess energy goes into the surroundings, and that's the damage that excess energy caused. Energy to the surroundings. The surroundings were completely destroyed in that case. There. We call this what type of? When we're talking about energy, what is this? This is a exo or endo. This is exothermic. So we looked at just 2 exos. Give me an example of an endothermic. Photosynthesis. That's a good one. Photosynthesis. So if we were to map this out, like in terms of energy here on the y-axis, now this is kind of an arbitrary energy scale. I don't have any numbers here. I'm just looking at relative position. So are we lower in the energy scale or higher in the energy scale? That's all I'm looking at. And the exact distance or whatever else depends on the numbers here. Since there's no numbers, it's still all relative. And so in photosynthesis, we're starting off with CO2, 6 of those, plus 6 H2O. Now CO2 is a gas, H2O is a liquid. Because this is photosynthesis occurs close to room temperature, 25 degrees C. And so, and then what is it making? What do the plants make? Plants are going to make this C6H12O6. You recognize that? Good. That's glucose. Or if you link them all together, we call it, depending on how you link them, but plants would link the glucose together to form cellulose, which is this wood. And what else do plants produce? Oxygen. So we'll have 6 O2s here. And so when we look at this, a mixture of sugar and oxygen is going to be at a higher chemical potential than water and CO2. And here we know that because sugar, we can caramelize it. We did it with sucrose, not glucose, but you can do the same thing. You kind of burn it, partially burn the sugar, caramelize it. Or you can completely burn it to turn it into charcoal, or completely burn that to turn it into CO2. And so we can burn the sugar. In fact, this is what we do. We do the opposite. We do the opposite process because what we do is we eat sugar and we breathe in oxygen. And then we end up exhaling CO2 and producing water in the process. And so we do the opposite, and then we use the energy that comes from that process. And the plants do this. The plants will take the CO2 and the water and convert that into glucose and O2. So where does the energy come from here? The energy must come from the surroundings. And where is it from in this case? Yeah, the sunlight. Energy from the sun can come in here and do that. Now, when we look at this, is this a change in, because this will be at 25 degrees C, is this a change in potential energy, chemical potential energy? Yeah. And so this delta E is equal to a change in chemical potential energy. So the chemical potential energy went up. Well, how did it go up? Well, it got energy from the surrounding. What about the kinetic energy? Was there any change in the kinetic energy? No. And so delta KE is going to be 0 here. So this is the way we do it. You know, sometimes, you know, in like combustion, there's going to be both, a change in potential energy and a change in kinetic energy. Because, for example, when we combust the methane, it's going to get hot. And so if it gets hot, then there was a change in both potential energy and kinetic energy because the temperature skyrockets up. Right? But, you know, we can do both. We could do both, but the thing is, eventually it's going to cool down. Is it going to stay hot forever? No, the temperature is always changing until it's going to stop. Where does the temperature stop? At room temperature. And so basically the temperature is going to skyrocket. And so if you pick one of these temperatures, it's just on its way down. In the next minute or the next second, the temperature's changed. The temperature continually changes. And therefore, you know, if we pick some arbitrary temperature, then it doesn't really make sense. You know, we could go to 1,000 degrees. Maybe we pick the peak temperature. We could do that as well. But to keep things simple, this is the way we do it. When there's a chemical reaction like this, you know, or you know, a chemical change, then we like to think in terms of just potential energy changes. And so chemical change, we like to think in terms of potential energy and keep the kinetic energy the same. So both of these are chemical changes. When there is a physical change, it depends on the type of physical change. We have two types of physical change. And we'll get into this later, but like hot water cooling or cold water warming, you know, there we like to keep the chemical potential change at 0 and just think in terms of kinetic energy change. And so, like the previous example with the water cooling down, that's just a physical process. You know, call it heating and cooling objects. This is a chemical process in which we're doing some reactions here. All right, so there's conservation of both matter and conservation of energy. Here, the conservation of matter is, you know, we start off with 1 carbon atom, we still end up with 1 carbon. We have 4 hydrogen atoms. Now those 4 hydrogen atoms are attached to oxygens to form 2 waters. And we have 4 oxygen atoms. 2 of those end up in carbon dioxide. 2 of them end up in the 2 waters here. And so we have conservation of matter, or conservation of mass, because the atoms are just rearranged. And then we also have conservation of energy here. As the energy goes someplace into the surroundings, or comes from someplace from the surroundings. And the surroundings are just generic. Whatever surrounding this is going to get hot, or whatever surrounding this will get cold, depending on if it's endothermic or exothermic. All right, what else did we talk about on Thursday? the laws of conservation of mass and energy. Anything else? Chemical equations, yeah, that's good. What do we call this? If this is the starting mixture, we call that the, and this is the final mixture, we call it the product. And usually we'll just show an arrow, so reactants going to product in one line. And so here's the photosynthesis in terms of chemical reactions. Now energy, sometimes we include energy in the equation, sometimes we exclude it. You know, just look at it this way. It depends. You know, and it's just for compactness, and sometimes the amount of energy is not the most important aspect of it. But we have chemical equations. What I did with mine is I put in the states, like gas, liquid, solid, because that makes a difference in the amount of energy. You know, so for example, if you're forming gaseous water, is gaseous water at a higher energy or lower energy than liquid water? It's at a higher energy, so it makes a difference whether we use liquid or gaseous water here, because it's going to change the amount of energy that's produced. And so we need states in here whenever we talk about energy. But other than that, this is a chemical equation. Okay, well, what else did we talk about?
The law of multiple proportions.
The law of multiple proportions? Okay, that's good. What did we say about the law of multiple proportions?
Parts of the compound to form the atoms must go up in molecular ratios and have like part of the atom.
Yeah, that is the law of multiple proportions. That's good. But is that all? Was there more to it? Uh-huh.
That it was the same as the law of constant.
Yeah, it's the same as the law of constant composition. The law of constant composition, the law of multiple proportions, same thing. Yeah. What else did we say about it?
The weight ratio of the elements in the compound are fixed.
Yeah, the weight ratios are going to be fixed because the atoms, if they occur, you know, like I said, something like water. We look at it. I don't know if I said this, but water is 11 or 12% hydrogen by weight, 88% oxygen by weight. Just because the oxygens weigh a lot more than hydrogen. Hydrogen is very light enough. So that the weight ratio is going to be fixed. Sure. But you know what else? I didn't say anything else about it. Where did most laws come from? Where do most laws come from? From theory?
Yeah.
Do you agree?
Observation.
Or observation?
Observation.
Well, it turns out most laws actually come from observation, but some laws can be derived from theory. Where did the law of multiple proportions come from? Yeah, atomic theory. And so this is one of the successes of atomic theory. You should know that the law of multiple proportions is one of the successes. It's just further evidence that atoms do exist. And proving it was very difficult in Dalton's time, right? And so the law of multiple proportions offers significant evidence for atomic theory and the absence of instruments to actually see atoms, right? So that was the take-home message. So that was the connection between the scientific method and that. Even though scientific method was discussed in chapter 1, it was brought up again because, you know, the more we see this stuff, the more connections you can make, you know. And so this is why you want to review. You want to review, and if there's anything that's doesn't seem so significant, you want to make sure, you know, is that significant or not significant? Because otherwise you should know everything that was discussed. And so just make sure. It's not so hard to know everything, you know, there are a whole bunch of things. It's not so hard to know everything. because it's not like you're okay. All of a sudden, my New Year's resolution. I'm going to start exercising. That's my New Year's resolution. So the next day, you join a marathon, right? You join a marathon. It's going to be a huge struggle, especially if you never exercise. Let's say I don't exercise enough. I'm going to do a marathon. As my first step. You don't do that. What you do is you slowly build up, and as you slowly build up to it, then once you've trained your body to do it, then you can do it, the marathon, right? But getting up to that point is it. And so this is the way it was like. This is the way I used to study. I used to study was like, okay, I'm going to do a marathon in one night. I'm going to just cram everything for the exam the next day. And that didn't work. Versus I switched it and started reviewing. If you review your notes every day, then anything that doesn't, as long as your notes are complete, then it's easy to remember everything. It's easy because it gets old after a while. It's the same thing. It's like kindergarten. If you go back to kindergarten, everything would be so easy, wouldn't it? This is just because you built up on it. Maybe kindergarten was easy, maybe it wasn't easy at the time. But you build up knowledge, you build up understanding, you build up that kind of stuff. And so the same thing here. You can make these connections, like the connection between law of multiple proportions. Automatically you should be thinking, okay, most laws come from observation, but this one didn't. Can you name another theory, derived law, the law that came straight from theory? What are all the laws that we covered so far? Can you name them? And so these are the things that will pop up, with review. So, did we talk about anything else?
Well, we talked about the prefixes and like compounds like methane.
Oh, meth, F,
Yeah.
pro. Okay, that's just straight memorization. We need to memorize those. But pretty soon you'll see a pattern. Methane, methanol. What does methane and methanol have in common? They have one carbon, yeah. How many carbons does ethane have? 2. Yeah. How many carbons does ethanol have? 2. Yeah, so that memorization you want to get down as well. Did we talk about anything else?
We talked about how noble gases are very reactive. So
Good, yeah. That's chemical knowledge. Noble gases aren't very reactive.
and nitrogen is a pseudo-noble gas.
Nitrogen is a pseudo-noble gas. Right. Yeah. That's good. Nitrogen is very unreactive, so it's treated as a pseudo. It's a bit more reactive than the noble gases. What are the noble gases? Helium, neon, argon, krypton, xenon. Those are all stable, like the Nobel metals. What were the Nobel metals? Gold, platinum, very stable. Which means they have high chemical potential energy or low chemical potential energy at room temperature? Very low, very low. Low, actually I should have written that. I forgot to write this out. High chemical potential energy means very reactive. Or high reactivity. Low chemical potential energy means less or lower reactivity. I should have did a parallel statement, but it's all right. High reactivity, low reactivity. In terms of stability, high chemical potential energy means less stable. Low chemical potential energy means more stable. And so the noble gases have very low chemical potential energy. They're very stable. They're very unreactive. And so nitrogen is a pseudo-noble gas, so it means it's very reactive. Gold, very unreactive, very stable. This is why gold retains its luster, whereas most metals start to corrode and discolor. And so these are the types of connections you start to make as you review this, because as you review this, then you go, okay, this is connected to that. But however, you don't really see the connections until you start memorizing or inputting, or getting the knowledge into your brain, because, a lot of people, they just jump right into the marathon and they can't really, it's just a struggle just to keep up as is. They can't really do much versus the people who train for this type of stuff. And so you're just training. You just think of it as exercise, it's just training your mind for chemistry. That's what you need to do, and then you'll be at the lead of the pack. You'll be way ahead of most people, because most people are just going to jump right into it. All right, then what? Was that it?
Electrical forces study in chemistry.
Yeah, electrical forces. Electrical forces are most important in chemistry. This one, In fact, if we measure the strength of the electrical force here, we can come up with a new law. Do you know what the law is called? This is called Coulomb's law. Coulomb's law is the force of attraction that's generated. We'll talk more about Coulomb's law later, but that's another law that came from observation, not theory. What is a theory? What is the theory of electricity?
That like forcing propel and opposite forces attract.
Okay, is that really a theory? Is that really the fundamental? Well, I guess you could say in a way it is, But like charges attract opposites, or like charges repel, opposites attract. That's observation for sure. But once you get into the theory would be, okay, what about like charges makes them repel one another? You would try to dig deeper into it to get a more fundamental understanding. But it could already be at the fundamental level. But anyway, we'll talk more about that. That's more physics, realm of physics, but this is very important because electrical forces are, as was mentioned, electrical forces are, everybody should know this, electrical forces are electrical forces will, this is why like water molecules stick together. Water molecules stick together because of these electrical forces, right? That's what I talked about when we were looking at this slide, I think. I was talking about water sticking together. This is because of electrical forces. But electrical forces versus what type of forces? There are other contexts. These contexts you'll know because you've gone through it many times. And so electrical forces versus, well, chemists aren't that interested in gravitational forces because like an oxygen molecule down here versus an oxygen molecule at the ceiling, there's so little difference in the gravitational energy because of the mass. It's not very massive. So, if I have an oxygen way up there, I don't worry about that oxygen falling and hitting me on the head because its mass is nothing. So chemists aren't that, unless a chemist is going to go to the moon. Let's say one day you're on Earth, the next day you're on the moon, then you start to worry about gravitational forces. This is why chemists are bad in the sense that chemists tend to use mass and weight interchangeably. Physicists won't do this. To a physicist, mass and weight are two totally different things. But to a chemist, it's close enough because a chemist stays here on Earth. And so do you know what the difference between mass and weight is? Well, I jump ahead a little bit. This is in the next chapter. Let's see this. Mass is the quantity of matter. And so your mass on Earth versus your mass on the moon will be exactly the same because it's the same quantity of matter. However, your weight will be different The weight is the force of gravity acting on the mass. And so your weight on Earth versus your weight on the moon will be totally different. In fact, your weight on the moon will be 1/6 your weight on Earth because the gravitational force is like 1/6 that of the Earth. But the mass will be the same. So, and we use kilograms or grams for mass. We use pounds or ounces for weight. But since the gravitational force doesn't change much, let's say I have a lab here and a lab in Colorado, the gravitational force is a little bit different, but it's so small, it's negligible. And so the weight doesn't really change from here to Colorado. And therefore, the weight doesn't really change much. We use them interchangeably. What was I talking about then? Talking about electrical forces versus gravitational forces. Gravitational forces we tend to ignore completely. You worry about it if you got when you worry about it is if you have a bottle of highly reactive chemical stored precariously on a shelf well above the floor. This highly reactive chemical can fall off the shelf onto the floor and cause a bad reaction. That's where we worry about gravitational. So when we store chemicals, we've got to worry about if an earthquake hits or whatever else. We don't want things with high chemical potential energy to react. I guess there's some typhoon, and I just read this article. There's a typhoon in Japan, so I saw this article that said 100 cars caught on fire. So I was thinking, how did cars catch on fire when there's some kind of typhoon? So I didn't figure that out. But anyway, so gravitational potential energy is not that big. We worry about electrical forces, and I said the electrical forces are the most or least important in chemistry. They're the most important in chemistry. Unless, of course, you're what type of chemist? If you're this type of chemist, then it's not the most important. If you're this type of chemist, then what's more important than electrical forces? Nuclear. If you're a nuclear chemist, then you worry about nuclear forces. Nuclear forces are different than electrical forces. And so those are the types of things I talked about. Those you maybe others. And so what you want to do is you want to compare with your friends, make sure you have everything, and then just review it. Review it repeatedly. If you review it repeatedly, then all this is going to be a lot easier. A heck of a lot easier to deal. All right, let's take a look at the next chapter, chapter 3. Chapter 3 is a long chapter and deals with measurements and calculations. There are a lot of learning objectives in this chapter, so let's quickly go through these. Scientific notation, a big one. And then we have something called conversion factors. Conversion factors are used in the way we solve problems. They come up with an algorithm. This algorithm that's used for solving problems, I call dimensional analysis. It's just a method of problem solving that we have. And so we have scientific notation, and we have something called dimensional analysis, which is used to solve most chemistry problems. When we talk about metric system, measurements, then some metric units like kilo, centi, milli, etc. We distinguish between mass and weight. Then we identify metric units of mass, length, and volume. We have some prefixes here, metric prefixes. And we'll add some more like micro, nano, pico, etc. And then do some calculations here. Then in 3.6 we talk about something called significant figures, and uncertainty and significant figures, rounding, metric to English conversions, Celsius to Fahrenheit, etc. And so a lot of learning objectives. The first part of this deals with scientific notation. We express big numbers and small numbers most compactly in terms of scientific notation. Is everybody familiar with scientific notation? Pretty much. You know what the coefficient is? The ABCD part here. And then we have the exponential, 10 to the e, and then the exponent. Exponent is the e part of it, what it's raised to. Exponents are usually whole numbers, although they don't have to be. If you have a calculator, you know. But when we express this in terms of scientific notation as the final answer, it will be in terms of whole numbers. Coefficient exponential. So we can convert from decimal to scientific and vice versa. Some updates here. So let's look at some conversions here. Convert 3,672,199 to scientific notation. How do we do that? We'd have to move the decimal point. 1, 2, 3, 4, 5, 6. So it would be 3.672199 times 10 to the 6. So if we make this number smaller, we make the exponent bigger. So it's going to be 3.672199 times 10 to the 6. So make this number smaller, the exponent grows bigger. Now this is a small number, so we're going to make this number bigger. That means the exponent has to go smaller. So we're going to move this 1, 2, 3. And so we moved it 3, so we made it bigger. So we're going from 0.0461 to 4.61. That means the exponent has to go smaller. It's going to -3. And so the rule is, if you summarize this, I don't know, I just say make the number bigger, exponent grows smaller, make the number smaller, exponent grows bigger. And this is a take home. They say 4.61 is larger than 0.0461, hence the sign is negative. Whatever you do, you just come up with some simple way of remembering. Okay, conversion of scientific notation to decimal. So the same rule applies for me here. Okay, I want to make this bigger because I want to go from -11 to 0. 10 to the 0 to 1. So I got to go from -11 to 0. So I make the exponent bigger, therefore I have to make the number smaller. So I'm going to make this one smaller. So by 11 decimal places, 1, 2, 3. So this is 11, and then I'm going to add a leading 0 here. This one I need to make the exponent smaller. I'm going to go from 4 to 0. Going from 4 to 0, if I make that smaller, this number has to grow bigger. It's going to be 51,600 with a 4 over. So this is all pretty basic review. It should, but if you need some additional practice, there's additional practice in the supplement and in our book. How you key it in. How people key in scientific notation varies. But if you have an EE or an EXP key, that's the best. You don't want to use this. Let me show you. We decided to get this 115 ES. Take a look at the keyboard here. It's on which key. All right, there are different keys. It depends on your calculator, how you do it. And so we look here. On this one, it's not an EE or an EXP key. It's this one at the bottom. Do you see the one at the bottom next to the answer? It's times 10 to the x. Some calculators have this key. It's not the times 10 to the x key, it's the 10 to the x key. Have you seen calculators with this key, 10 to the x, versus EE, which is equal to EXP, which is equal to times 10 to the x? There's a difference here. This key here, times 10 to the x, is not the same as this one here. Do you know what the difference is? This one is scientific notation. This is what we call the anti-log base 10. The anti-log base 10, what happens is people use this key here. When they use this key, sometimes they're off by 1 order of magnitude. Let's say it's supposed to be 10 to the third, they get 10 to the fourth. And so they're off by 1 order of magnitude because of how they key it in. So when you're doing scientific notation, if you hit the E, EXP, or times 10 to the x key, all you need to do is input x here. If you hit this key, then it means a different thing. Does that make sense? Or some people will hit the x to the y key. The x to the y key, which is shown here, this would be the x to the y key here. They input, and then they plug in 10 for x and then put in the y value. There. Well, all those are wasting time, and a lot of exams are timed, so you don't want to waste time. You want to do the minimum keystrokes for each of your input. And so it depends on your calculator. Different calculators will have different input methods. And so if I look at the TI also has a different, like a TI-30X, also has a different input method as well. And so you have to get familiar with this one. You see, it's different. In a TI-30, you have to use the second function here, second, and then you have to use this one, the x to the minus 1, to get you the double E. And so if you need to do scientific notation, it'd be second and then double E. Here, the x to the minus 1. Well, anyway, just normally we can catch any input errors early, just by seeing if you're off by a factor of 10 or how many keystrokes you have to do to input a scientific notation number into your calculator. All right, this is the dimensional analysis. This is a technique that we use to solve many chemistry problems. Many chemistry. In fact, the majority of chemistry problems you're going to encounter can be solved using this technique, algorithm, method, whatever you want to call it. This is dimensional analysis. Let's take a look. In dimensional analysis, we're going to use something called a conversion factor. So, there. And so whenever we have a number, it's not just a number, but there's a dimension to it, a unit to it. And so, for example, 50, it's not just 50, it's 50 minutes. And so this would be the dimension, and this would be the quantity here. So in dimensional analysis, we look at the dimension that we're given, minutes here, and then we look at the dimension that's desired. And so we want to express 50 minutes in terms of seconds. And so what we have to do is we're going to go from the dimensions of minutes to seconds. And so there's a pretty standard technique that we're going to use to get there. But what I'll do here is we'll stop here, read, and then we'll take a 10-minute break, and then we'll start again after that.